Hello everyone, welcome back to the channel. Today we are taking a deep dive into one of the superstars of the linear algebra. They are called as the singular value decomposition, or they are also called as SVDs. So as I have said already, they are called the superstars of algebra, and they are nothing but our SVDs. First off, SVD is so important that smart people like Professor Gilbert Strang from MIT call it the fundamental theorem of the linear algebra. Okay, what is that? It is also called as what? Fundamental. Let me write it down. It is a fundamental theorem of linear algebra. But why? Because you might have this question, but why? Because it's very incredibly versatile. So unlike some other cool matrix that only work for the square matrices like eigen decomposition, which you might have heard of in my previous videos, SVDs, so I will write it down. So square matrix only works for what? The eigen decomposition. SVDs works for any matrix. They might be tall, they might be wide, they might be square, whatever. And the best part, it always exists. Okay, best part is what? It always exists. You can always find the SVD for any matrix. That's a huge deal in math. Okay, so when I say SVDs, the first and foremost thing what we have to know is their formula. The formula is A is equal to U sigma Vt. So let us dissect everything one by one. So U is nothing but it is also called as a left singular vectors. Okay, left singular vectors. So let me write all the points and what are the features of the U as a bullet point. Okay, so U can be, this is also an M by M matrix. Okay, you have to think U as the output space rotation matrix. Okay, this is very important. U as the output space rotation matrix. Its columns, that is for example U1, U2, U1, U3, so on up to M, are special vectors called the left singular vectors. Okay, they are also called as what? The left singular vectors. So the crucial point is that U is an orthogonal matrix. That's fancy math talk for a matrix whose columns are all perfectly perpendicular to each other and each column has a length of 1. Okay, what it basically means, U only performs, okay, this is very important, it basically means U only performs rotations and reflections. Okay, it doesn't stretch or they doesn't squish anything. Okay, they don't contract or relax. It just changes the orientation in the output space. Okay, what does it change? It only changes what? The orientations in the output space. Now let us go to the second part. What is that second part? That is the sigma, right? In the formula, what is second part? Sigma. So sigma is also called as a singular value. Okay, so the singular values. So this is the heart. Okay, this is the heart of the scaling. Sigma is an M by N matrix. So what was U? U was M by M. This is sigma is M by N matrix, but it's super simple. It's almost all zeros. The only non-zero values are on its main diagonal. Okay, on its main diagonal. These diagonal entries are called as singular values. Okay, whatever the diagonal entries you have, right, they are called as singular values. They can be represented by sigma 1, sigma 2, sigma 3, so on up to sigma n. Okay, so on up to sigma n. So these are always non-negative numbers. This is very important. Again, these are non-negative numbers, meaning they are 0 or positive. So what they do, this is important, right? What is the functionality of sigma? These singular values tell you how much stretching or squishing happens. Okay, how much stretching or squishing happens. Almost the most important directions. The larger the sigma value, the more that direction get stretched. Okay, more that direction gets stretched. For example, the order matters. Okay, here, okay, let me write it down. So what they do, how much stretching and squishing will happen. So now what we have to do is So the main thing that we have to know here is that the order matters. So what do you mean by order matters? By convention, we always list them in the decreasing order. Okay, decreasing order in the sense sigma 1 is greater than or equal to sigma 2, and sigma 2 is greater than or equal to sigma 3, and so on. Okay, this means that sigma 1 represents the most significant stretch or direction of variation. The most significant stretch is what? Sigma 2. So lesser than that is sigma 2 and sigma 3. Okay, now the last part that you have to we are going to see is the V transpose. So V transpose is called as the right singular vector. So U called as the left singular vector, V transpose is called as a right singular vector. So this is applied for the n cross n matrix. Okay, think of V transpose as the input space rotation. What was U? U was output space rotation. V will be the input space rotation. Okay, its columns, or rather the rows of V transpose, which are the columns of V, are special vectors called as a singular vectors. So just like U comma V, and thus V transpose is also called as a orthogonal matrix. So it is also important. It performs rotations and reflection just like the U. Okay, if you see U and VT, it is almost similar. And in the input space, here it is applied for the input, and U will be applied for the output. So it sets up your vectors in the perfect orientation before they get scaled. Now the important thing that we have to so we have seen the dissection of the definition. Now let us see the theorem. Theorem is important, right? Now what does the theorem says? Theorem says that of the SVD theorem. Theorem is nothing but let A belongs to R n cross n be a rectangular matrix of rank R belongs to 0, m minimum of m, n. The SVD of A is a decomposition of the form A is equal to U sigma V transpose. Okay, so this is we have seen everything in detail. What is U, what is sigma, what is V transpose, we know everything, right? Now we have to know something very important is what is sigma. So sigma is it is a very crucial point. Okay, sigma matrix itself is unique. This is a super important while there might be different ways to arrange the columns of U or V, the actual value of the sigma, that is the singular values, are always the same. Okay, always the same of a given matrix A. Okay, it's like the DNA of the transformation. Now let us take scenarios. Okay, scenario 1 is what I am taking. For example, a tall matrix. What is a tall matrix? A tall matrix is it is tall and skinny. What does it mean? Meaning it has more rows, that means m, and less number of columns. Okay, that is less number of columns, n. Say for example a matrix 5 cross 3, 5 rows and 3 columns. Okay, so what matrix will look like? Let me write it down. Sigma is equal to sigma 1 sigma 1 0 0 0 sigma 2 0 0 0 sigma 3 0 0 0 0 0 0. So what is the thing that you are seeing here in a tall matrix? In this case, the singular values, that is sigma 1, sigma 2, sigma 3, will sit on the diagonal of the top left part of the matrix. Then rest of all the rows will be filled by entirely with the zeros, right? If you see the top part, you can see that sigma 1, sigma 2, sigma 3, they're sitting on the top left part of the matrix. Rest all the numbers are 0. It's like having a small square diagonal block and then just tracking on rows of zeros below it to match the height of the A. Now this is all about tall matrix. Now what we have, the wide matrix, that is in case of length. Suppose what is a wide matrix? Wide matrix is nothing but it has more number of columns and lesser number of rows, right? So let me take an example of a 2 cross 4 matrix. Okay, 2 cross 4 matrix. 2 cross 4 means we will have only 2 sigma values. There's sigma 1 and sigma 2, right? Where they will sit now? Sigma 1 0 0 0 0. How many columns? 4 columns. All right, let me write it down. So yeah, 0, sigma 2, 0, 0. Now see the singular values sigma 1 and sigma 2 will sit on the diagonal of the top left part, and the rest of the columns to the right will be filled with zeros, right? To the right everything is 0, to the left I have filled with the singular values. So it's like a small diagonal square block with columns of 0 added to its right to match the width of the A. Now let us see everything with the problem, so that way we will be able to understand, and let's see the advantage, disadvantage of eigenvalue, eigenvector, everything in the next video. Thank you.